Thank you. So, as I said, I have the good fortune to introduce a rocket scientist. Not many of us get to do that, um, but I have the good fortune of introducing Marc Finkelstein to us tonight. Marc has a bachelor's degree of science electrical engineering from the City College of New York. He has a Master of Science in Nuclear Engineering from the University of Michigan. He has a Master's of Science in Electrical Engineering from the University of Michigan. And he has a postgraduate diploma in economics from the University of London. He's worked a number of different places. He's worked at the Lawrence Livermore Laboratory in laser fusion. He's worked at the ESL doing space systems assessment. He's worked for TRW Incorporated, working on infamous space and with the technical group. And he's been the chief scientist at Hughes Aircraft and president of Flight Science. Marc is now retired from flight science, but he and his wife, Susan, have made their home here in Juneau, and we're very pleased that they have. And he is an aerospace education officer for the Civil Air Patrol. And he's going to be talking to you a little bit tonight, I hope, about the Civil Air Patrol. I had the opportunity to go and visit down there at the airport, and it was fascinating. So he's also a pilot and a flight instructor. So his talk was really well received last year, and I'm sure tonight is going to be the same. So welcome, Marc.
Thank you for that introduction, Karen. Can you hear me okay? Is that going to stay there? Okay. So I'd like to say a couple of words about the Civil Air Patrol. Let me just organize this thing a little bit before I do that. Oops. I don't have a mouse here. Okay. So the Civil Air Patrol, I'm the aerospace education officer for the Southeast Alaska Squadron of the Civil Air Patrol. And Civil Air Patrol is an all-volunteer organization, and we have a community outreach mission, which includes talking about aerospace topics and really STEM topics in general. So CAP has a search and rescue mission, and it has an aerospace education mission, as I've already said. And it also has a youth leadership mission, and we train cadets in CAP. CAP saves about 75 to 100 lives a year around the country. That's not just downed pilots, but it's also hikers and boaters and hunters and what have you. If you think you might be interested in CAP, or if you have children ages 12 to 18 who might be interested or benefit from becoming cadets in CAP, I'd really encourage you to pursue that. And if you just Google Civil Air Patrol or gocap.com, gocivilairpatrol.com, it'll take you right there and it'll give you contact information. So with that, tonight's talk is really about space, and it's space at the smallest scale and it's space at the largest scale. Oh, there's my mouse. Let me just get this set up here for me. And how space is really interconnected with us. So back around 460 BC, the philosopher Democritus said, "Nothing exists except atoms, empty space, and opinions." And the real question is, was he right? And a more philosophical question is, what really is existence? What do we really mean by that? So coming from an aerospace engineering background, I take a very pragmatic approach to that. And by the way, do you guys know the difference between an optimist and a pessimist and an engineer? Anybody know that? Okay, well, an optimist thinks that the glass is half full. A pessimist thinks that the glass is half empty. An engineer thinks that the glass is twice as big as it needs to be. So if you're an old timer like me, this is the picture of an atom that you probably grew up with. It's a central nucleus of particles called protons and neutrons, and it has all these electrons spinning around it like little moons. The only problem with that is it's really not like that. So if you were to take an atom and you were to take the nucleus of that atom, where the protons and the neutrons are, and you were to expand that tremendously to the size of a marble, and you were to put that marble on the 50-yard line at Michigan Stadium, I'm partial to the University of Michigan, you would find that the electrons from that atom are out in the parking lot. Really, an atom is almost totally empty space. Only about 1,000th of a trillionth of the overall diameter of the atom is in that nucleus. So you have this thing where everything is made of atoms, we're made of atoms, and an atom is almost completely empty space. So okay, if that's the case, and if only the most minuscule part of the volume has any stuff in it, and we're made of it, and stone walls are made of it, then why can't we walk through stone walls? I mean, it's a legitimate question. After all, the chances of two parts of an atom, one of our atoms and a stone wall's atoms, hitting each other are unimaginably small. And if they do, so what? Well, we can't walk through walls because an atom and us and the universe is really not empty space. All space has stuff in it. And in the case of this example with the atoms that belong to us and the atoms of the wall, these electrons are negatively charged and they create a repulsive field. So our atoms repulse the atoms of the wall and we can't walk through walls. I don't know if that's fortunate or unfortunate. So to understand more, we've got to take a step backwards in time here. And on October 30th, 1961, on the archipelago of Novaya Zemlya in the Soviet Union, an event occurred. It wasn't the first of its kind, but it was by far the biggest, and it remains the biggest of its kind to this day. The Russians called it RDS-220, and the rest of the world called it the Tsar Bomba. It was a 50 megaton explosion, and interestingly enough, it's probably the most recurring event in the universe. And it's a very good thing, because the physical processes of the Tsar Bomba are exactly the same physical processes of our sun and almost all the stars in the universe. And it's these physical processes that make the stuff that makes us. So like most stars, the sun operates by converting hydrogen into helium, along with some heavier elements, and we're made of those heavier elements as well, and plus hydrogen, because H2O is water, and we're 70% water. So it does that in a nuclear fusion process like the Tsar Bomba, but the sun generates a lot more energy than any nuclear weapon or any nuclear explosive. In fact, it generates roughly 2 billion Tsar Bombas per second. And like the other 100 billion or so stars in the Milky Way galaxy, it gives us light and it gives us warmth to us and all the planets and all the stars that surround them. And this is really the light side of the universe that we're going to be talking about first. So a hydrogen atom is the simplest of all possible elements. It has only two components. It has a single proton in the center, and then it has a single electron. Meanwhile, a helium atom has two protons and two neutral particles called neutrons. So in order to turn hydrogen into helium, you have a multi-step process that involves changing two of the protons into neutrons. And that involves a tremendous release of energy, and you saw that with the Tsar Bomba example. And it also involves creating another particle called a neutrino that we'll talk about later. It's an extremely violent process with multi-million degree temperatures, and it streams material, the sun streams material out into space all the time. And this streaming of material is called the solar winds, and the solar winds go out in all directions, and some of the solar wind comes towards Earth. And we have to deal with that. And in some cases, it's very pleasant, like the aurora, and in other cases, as you'll see, it's not so pleasant. So every once in a while, a massive burst of material comes out of the sun. It's called a coronal mass ejection. And these things happen from time to time, and fortunately, most of them happen in a direction that doesn't head towards Earth. But every once in a while, one will. And we call that a solar storm. So to understand what happens next, you have to realize that the Earth is, amongst other things, a big bar magnet. Okay, it has a magnetic field, and we know that because our compasses point to magnetic north. And it happens to be one of the things that makes life possible, because that magnetic field shields us from the solar winds, and it shields us to a fair extent from the larger coronal mass ejections. And the shape of the field, I don't know if they still do this in high school or middle school, but you ever see a bar magnet and they sprinkle iron filings on it, and you see a picture that looks like that. And that happens on Earth too. And one of the things that you might realize is that some of those field lines, if this pointer will work, and it does, some of those field lines converge to the north and south magnetic poles, which are not the same as the north and south poles. And when that happens, these trapped particles that come in from the solar wind are allowed to come down into the upper atmosphere, and they energize the air in the upper atmosphere. And as the upper atmosphere releases that energy, we see that as aurora. So magnetic fields make streams of charged particles. And if anybody's still got an old TV set, you know, the real thick kind with the cathode ray tube in it, or an old computer monitor, if you could dig it out of the garage, turn it on, put any image you want on it, and hold a magnet right in front of the screen, any magnet. And what you'll see is the electron beam from that cathode ray tube is deflected, and you'll see this circular deflection. And the same exact thing happens on Earth. This won't work with a laptop, and it won't work with a modern TV. It's like a boat moving through water. The magnetic field creates a bow wave, and it also creates a wake behind the Earth. And the interaction of the solar wind and the Earth's magnetic field is called space weather. And space weather, to some extent, is predictable. And space weather, most days, like the weather, is pretty mild or reasonable. But sometimes space weather isn't so mild and not so reasonable. And the presence of this magnetic field around the Earth, by the way, is called the Earth's magnetosphere. And many other planets have magnetospheres as well, but not all. So when charged particles move in this magnetic field, they're deflected, and they basically curl around the magnetic field lines. And this is what happens to the solar wind as it interacts with the Earth's magnetic field. And they descend into the upper atmosphere, and we talked about this, and they generate basically the auroras. And you can see that, and it's beautiful, and everybody's happy, and everything is calm. But that is not always the case. Let me just track off to the side here. Besides the magnetosphere, space weather also considers another series of layers of the Earth's atmosphere called the ionosphere. And as the ionosphere is energized from the solar winds, then what happens is it becomes electrically conducting, and it'll actually reflect, if you will, radio waves. And old shortwave broadcasts, ham radio operators, and some military communications rely on that. And they get global communications basically by bouncing, if you will, signals off this ionosphere. And the ionosphere's activation goes along the same lines as the sun's magnetic field, which turns out reverses about every 11 years. And it's pretty regular, that reversal. So sometimes the magnetosphere can be overwhelmed. And when that happens, changing magnetic fields are induced in and create these large flowing currents. And if you have a long piece of wire, like in the power grid, like in the electric power lines, the longer the wire, the higher the voltage that's induced. And at some point, it overvoltages, and it can disrupt and take down large sections of the power grid, and you get these blackouts. And this has happened. We've seen this. Of course, we don't have history dating back 10,000 years because there were no power grids back then. But as we get more technologically dependent, our power grids become more susceptible because they become more computerized. And computers with 3-volt circuitry, like you have today, or even 1.5-volt circuitry, are particularly susceptible. And so we'll see outages both on the ground and in space, in spacecraft and in satellites, when we get these violent solar storms. So these storms, called geomagnetic storms, do occasionally occur, and they do cause mass disruption. And the flow of charges in the magnetic field works exactly like a generator, and I've just talked about this. And these higher than normal voltages can knock out the power grids. The good news on this is that we can see these solar flares erupting on the sun, and our vision of them, the light from these solar flares, travels at the proverbial speed of light, which is about 300 million meters per second. So it takes about 8.5 minutes for that light to get to us. But the charged particles that stream, the most energetic streams in the solar wind, they don't travel at the speed of light. They have mass. And so it takes 3 to 4 days for those charged particles to reach the Earth. So we typically get about a 3 or 4 day warning of the solar wind. Some things you can do stuff with that warning, like on satellites, you could turn them down. You can take them out of mission. Other things, like power grids, you're not going to shut off the power to North America because you have a solar storm. So you pretty much have to accept the damage. And these things have led to mass damage in the electrical grid. And here's a picture of some blackout areas, as well as some transformer damage that have occurred. This occurred in March 1989. And there was a particularly large solar storm on October 28th, 29th in 2003. And it took down power grids and it took down computers. And what's really interesting is you see a picture here. This is called the Halloween event of 2003. And if you look at that picture, that's of Houston, Texas. And what you're seeing is an aurora over Houston, Texas. And it was pretty prominent. So this is the real deal. So I'm not going to read all of these charts, but I am going to say just a couple of words about them. During that event, that Halloween event, these charts show the things that have happened, and you can see many satellites were either temporarily or permanently damaged. Astronauts had to go into radiation shelters in the International Space Station or in whatever spacecraft they were in at the time. Airline flights were diverted because of high radiation levels at high altitudes, and satellites are powered down. And by the way, if you want protection against any kind of electromagnetic pulse event or geomagnetic storm, the thing to do is to shut down electronics. Because if you induce 3 volts into a computer that runs on 3 volts, it can accept it if it's shut down. If it's going at 3 volts, then you're putting 6 volts on there, and it will damage it. So here's another chart, and you could read some of the things that have happened. Here's a third chart. This is all the same event. And you can see the damage is quite consequential. Now, some of these things are called single event upsets. That is, you just have to reboot the computer afterwards or you're in good shape. Some of these things are actually damaging, and satellites are taken out of mission permanently. And power grids, of course, can be repaired on Earth, but it could take some time. So here's something else that's very significant that's happening, which has nothing to do with the solar wind, but it certainly affects how the solar wind is affecting the planet Earth. And that is the magnetic field on Earth right now, as we stay here, stand here, sit here, is reversing. And these things happen. This is not the Earth flipping upside down. This is not the zombie apocalypse. This is a magnetic field reversal. This happens on the sun every 11 years, and it happens on the Earth with a fair amount of regularity. And I'm going to try to bring up a laser pointer on the screen here, if I can do that. Now, can you see that okay? Okay, so if you look at the magnetic field, and the North Magnetic Pole is not the same as the North Pole. And it's been mapped out since the 1600s because ships navigate by the magnetic field, amongst other things, and people navigate by the magnetic field. And if you look at what's happening here, so this is, let me get that on there. This is circa 1600, and for 100 years the magnetic field moved that much. The next 100 years it moved that much. Now this is a large piece of terrain you're seeing here. Okay, from 1904 up to 2010, this is just a little more than 100 years. This is 106 years. the magnetic pole has moved that much. And if you look at this, I'm going to use my laser pointer here. Let's see if that works. If you look at this bottom stretch here, every one of the black areas are the way the field is right now. And the light areas are the reversed field. And we see that there have been a number of reversals. This is millions of years ago. So you're going down to 160 million years ago here. And you can see these reversals happen. And they happen at an average frequency of about once every 200,000 years. And the last reversal, and these are not regular on Earth, unlike the sun, the last reversal happened 800,000 years ago. So we are past due. And we're seeing that happen. And you see two things that happen when the magnetic field reverses. One of the things that you see is the movement of the magnetic poles, and I just described that, and I just showed you that. The other thing that you see is a weakening of the magnetic field. It actually gets weaker, and it starts to basically disappear in certain areas of the Earth, and we're seeing that right now. And the area that you're seeing that's in blue up there, this area here, that's called the South Atlantic anomaly. And the magnetic field is the weakest on the planet there. And so it's the highest radiation dose. And as satellites go through that area, or airplanes go through that area, in the satellite case, oftentimes you'll turn them off. And there's been computer outages on the International Space Station as it's passed through that area. And there have been damage to satellite computers, so they are turned off. And they come out of mission, and then they're turned back on when it leaves the area. Now, this primarily affects low-altitude spacecraft, not the higher altitude. And some of the military spacecraft obviously are radiation hardened for reasons other than the solar wind, and they're not affected by this, but many are. So there's lots of speculation about this solar reversal. Recent measurements indicate that the weakening is increasing, and the field is about 3% weaker in the last decade alone. So we're not talking about million-year periods or long geological times. And we know this history of magnetic reversals because the magnetic field is trapped in lava as it hardens. So if you take a magnet and you heat it up hot enough, about 1,350 degrees or so, you get to a temperature called a Curie temperature, and the magnetic field of that magnet disappears. It's no longer a magnet. And then if it's in a magnetic field as it cools, it takes on the magnetic field of its environment. And so lava does this for us. And we know the age of different lava flows, so we know how often this thing happens. And again, this is happening. It is not the end of the world, so you don't have to worry about it. The zombies are not coming. So if you want to find out more about space weather and the light side of the universe in general, or find real-time information about whether there's going to be an aurora in Juneau, then go to a website. This is SWPC Space Weather Prediction Center.noaa.gov, or just Google space weather and you'll get to this website. And I got to get back to a pointer, so stand by, bear with me. Okay. So that was a quick look at space near the Earth and the Sun. And it also is a quick look at what space looks like in other star systems with planets. You know, we know there are a multitude of planets. I think we found 2,000 or so planets so far. I don't know what the exact number is at different star systems. So each one of those has space weather type conditions, just like Earth does. And again, some of the planets have strong magnetospheres, others don't. And one of the things that might be interesting to you is the planet that's in that sweet spot for life besides the Earth is Mars, and Mars does not have a magnetosphere. And so the solar wind has been able to, just by physical bouncing off the molecules of the atmosphere, these particles, erode the Martian atmosphere to make it very thin and not life-supporting. So this brings us to the dark side. And we're not talking about Darth Vader here, so there's a red bar through his face there. So the light side of the universe is the side that are near stars, and we're dangerously remarkably near a star. You know, the sun is about 1 million miles in diameter, and so we're about 93 diameters from the sun. We're about 93 million miles. That's not a far distance. I mean, that really isn't when you're talking about 2 billion Tsar Bombas per second going off at that distance. So the dark side, and again, we're not talking Darth Vader, is in the distant universe, 1 billion light years away, 100 million light years away, 1,000 light years away, where you're far from the nearest star. And the question then becomes, what's really out there? And obviously we can't see what's out there. If you put an asteroid 1 billion light years away, there's no way our instruments just aren't good enough. But we can see the effects of things that are happening out in deep space. And those effects don't quite jibe with our knowledge of physics, and we'll get into that. And again, just because we can't see something, touch it, or smell it, doesn't mean we can't see the secondary effects of it being there. You know, just kind of backtrack a little bit. Last year I gave a talk where I talked about the Higgs boson. We never saw a Higgs boson. It's got a life expectancy of 10 to the minus 23rd seconds, which is instantaneously gone. What we saw is the effects of the Higgs boson. And the same kind of thing happens here. It's not because life expectancy is short for these particles. It's just because they're so far away and they don't emit light that, you know, with our best radars and best telescopes, we just can't see it. So what I would suggest is we do a little bit of a thought experiment here. And I'll get my laser pointer out again. Take a look at this. Oops. Take a look at this cube here. It's a little hard to see. Just imagine that that's an arbitrary cubic inch of space sitting 1 billion light years from the nearest star. Now we could say, well, that's probably going to be pretty much empty space. But now think about this in this thought experiment. Put your eyeball right up against that cubic inch of space and look out. What do you see? You see all these galaxies. Okay, well, what does that mean, seeing all these galaxies? Well, what that means is that light from these galaxies is going through that cubic inch of space that you're looking through. Well, light has energy and light has information. It tells you things about the galaxy. You can find out, even with our current instruments, what these galaxies are made of, how fast they're moving, if they're rotating, how fast they're rotating. So in that cubic inch of empty space, 1 billion light years from the nearest star, there's all sorts of energy. There's the microwave, the cosmic microwave background. There's light from the stars. There's light that you can't see, like X-rays and gamma rays. So to understand this better, the next couple of slides are going to be a little bit of physics background. If you were here last year, you probably know this stuff already. So light waves, just like microwaves and ultraviolet waves and gamma rays and radio waves, are all basically the same thing. They're a time-ordered wave-type disturbance of the electromagnetic spectrum. The difference between these different waves are the wavelength. In other words, the difference between peaks. And you can see that there with a little example of water. You can measure the difference between wave peaks or wave troughs. And it's the wavelength that differentiates a radio wave from an X-ray, from a light wave, from a gamma ray. So in the electromagnetic radiation spectrum, an FM radio station transmits a wave that's about 3 feet between peaks. A microwave oven about 6 inches between peaks, and green light about 1/2 of 1/1,000,000th of a meter between peaks. And the famous physicist, Nobel Prize-winning physicist Max Planck discovered that the wavelength is inversely proportional to the energy contained in these unit packets of light that are emitted, and these packets are called photons. And that the shorter the wavelength, the more energy these things contain, these photons contain. So an X-ray photon contains far more energy than a radio wave photon. And a radio wave photon contains far less than blue light. And you get the idea. So we talked earlier about the fusion reaction in stars, and one of the things created from this is a particle called a neutrino. And a neutrino is intrinsic to the conversion of protons into neutrons and neutrons into protons. And a helium atom, which is the product of any hydrogen bomb or the Tsar Bomba or the sun for that matter, that contains 2 neutrons, 2 protons, and 2 electrons. And that helium atom is made from 4 hydrogen atoms that contain only a single proton each. So two of those things have to be converted from protons into neutrons. That's done with a force. It's one of the four forces in nature called the weak nuclear force. And we'll get into that in just a second here. But if you just hold up your hand for a second, you would find that passing through your hand is about let's see if I've got this right here. There are about 6 trillion neutrinos that pass through your hand every second. Okay, and since it's nighttime here, and these neutrinos are coming from the sun, because we don't have any nuclear weapons being detonated nearby, then they have to pass through the Earth before they pass through your hand. And what does that really mean? What that really means is that these things are capable of passing through anything, and that makes them extremely hard to detect. They're not impossible to detect, by the way, but they're very hard. So from 6 trillion neutrinos, you're lucky if you get one in a detector. But you will get some in a detector. They are detectable, and they do have a tiniest amount of mass. So they don't quite travel at the speed of light, but they travel close to it. So there are roughly 250 billion stars in the Milky Way galaxy alone. Forget about the visible universe. And almost every one of those stars is emitting massive quantities of neutrinos, which have almost no mass, but there's a massive quantity of them. So that kind of makes up for it. So most of us have heard of E equals mc squared, Einstein's famous equation, and it basically equates, and I really mean equates literally, matter with energy. Matter can be converted to energy, energy can be converted to matter, and matter has an energy equivalent, energy if you will. A little redundancy there. Okay, we know that we can convert matter to energy because the sun does it all the time, and nuclear weapons do it all the time. Nuclear reactors do it, and physics laboratory experiments do it all the time. And we could also go the other way. We can convert energy to matter. And one of the things the medical community has done is they've done positron tomography, which uses gamma rays that are sent near the nucleus of atoms, and they instantly decompose, if you will, or create, really is a better word, a positron and an electron. So this positron emission tomography machine basically takes energy from the gamma ray, and it creates matter particles from it. And from that, through some medical magic, you can diagnose conditions, and you could image the inside of soft tissues and hard tissues and what have you. So material in stars, you know, if I've got a material, whether it's a gas of hydrogen or helium or argon or nitrogen or whatever you want to put out there, what's going to happen is because of quantum effects in that gas, it's going to absorb certain wavelengths, and that absorption is going to leave fingerprints, and those fingerprints are going to be in the spectrum, the colors associated with that starlight. And so we can see those colors, and I'm showing you two up here. This is absorption lines from the sun, and this is absorption lines from a supercluster of galaxies that are about 1 billion light years away. And one of the things that you see here is you see these two lines here. What looks like two lines is actually three. What looks like a heavy dark line and another line next to it, that is shifted over here. And there's a line here that's shifted. This line is shifted. In fact, all of these lines are shifted towards the red. And so what causes that shift is something that's very common. Let's see if I can make that happen. That's the Doppler shift. And you hear that when you hear a train or a car blowing its horn. As it comes towards you, the pitch increases. As it moves away from you, the pitch decreases. And the same thing happens. Remember I said light is just waves. And the same thing happens. This red shift that you see here is basically caused by a galaxy moving away from us. And by noting the amount of redshift, it turns out it's a very easy calculation to determine the speed at which that galaxy is receding from us. Move my mouse over here. So one of the things that came up fairly early on by a now famous scientist, Vera Rubin, in the 60s, One of the things she noticed was that galaxies rotate. I mean, this has been known for some amount of time. And that the rotation rate of galaxies can be measured basically by measuring the Doppler shift. So the part of the galaxy that's rotating towards us is going to be shifted towards the blue. The part of the galaxy that's rotating away from us is going to be shifted towards the red. And if the galaxy is moving as a bulk towards or away from us, that whole thing is going to shift over appropriately. But there's a problem here. So she realized that if you use Newton's laws to calculate what happens or what the expected rotation speed is for an object in a gravitational field, an object rotating around the galaxy, like the Milky Way, what you find is you would expect that as the distances get larger, the rotation speed gets smaller. But guess what? It doesn't happen that way. The rotation speed is almost constant. And there's only two explanations for that. Okay, and you could take your pick on this. One explanation is there's a whole lot more stuff out there that we can't see, and we'll call that dark matter. And the other explanation is our physics are wrong. And it wouldn't be the first time. So way back when, Isaac Newton gave us the laws of motion, and he talked about the laws of motion and gravitation. And I will say these are empirical laws. I mean, he observed the acceleration of a gravity field, and he wrote an equation that mimicked that observation. But Newton's laws are really kind of a Goldilocks law, okay? They work for stuff where the speed isn't too fast, where the gravity isn't too high, where the size isn't too small. For that, you need corrections of Newton's laws called quantum mechanics and relativity and the theory of relativity. So it's not unusual to change known laws of physics. And about 100 years ago or so, maybe a little less than that, we've actually about 100 years, we had the theory of relativity and we had the theory of quantum mechanics, and they said, Newton's laws are fine for that intermediate range of stuff, but they're not fine when you're traveling near the speed of light. They're not fine if you have the mass of a star. They're not fine if you have the size of an atom. So here's Vera Rubin again, and she's doing these calculations in the 60s and 70s, and she says that galaxies are spinning so fast around their central core, especially the outer arms, not so much the stuff near the center. The outer arms, that Newton's laws would say they should be ripped apart and thrown into space. And so she hypothesized the solution that says our physics is right, and therefore there's a whole lot of matter out there that we can't see. And in fact, in order to make this work, there's 5 times as much dark matter than there is ordinary visible matter. So Vera Rubin's she suggested that this violates Newton's laws that I said, and she took the approach that this dark matter does exist, and the current majority opinion among physicists is that there is dark matter. And there's a bunch of reasons to, I'm getting a note here, restart your device to finish installing updates. Remind me later. Okay. Okay, so the majority of scientists accept the dark matter thing, but you got to be skeptical, because this halo of unseen, invisible, magical stuff that's around all of these galaxies should be around our galaxy too. In fact, it should be right in front of our noses as we sit here right now. And nobody's been able to find it. And I'll tell you, more than $1 billion have been spent on experiments trying to find dark matter, and nobody has found any. And when they do find the first particle of dark matter, I will be the first person to say, they were right all along. But so far, they have not found that. And I'm not ready to say that, because it's a tough pill to swallow. But there's another problem too, and that is a thing called gravitational lensing. And we see that through all the large telescopes. It generates rings around galaxies and multiple star images. And it's predicted by Einstein's relativity, because Einstein said that large masses, the gravity associated with large masses curves space-time. And if you curve space, then you curve the light that travels through it. And so you get this lensing. And in fact, we do see that. And you can see an image in the upper left of gravitational lensing. You see that through the Hubble Space Telescope. You see that through large ground-based telescopes. it's something that's very real. So to explain the faster than expected rotation rates, we go to this dark matter. So galaxies are far away, and maybe it's not really dark, invisible, magical matter. Maybe it's other stuff. Maybe it's just asteroids and comets and little planets and brown dwarf stars and neutron stars and stuff that we just can't see because it's too far away. But it doesn't explain the factor of 5. And that's a hard one to explain. So the problem is, to make sense of this, we know that this dark matter, whatever it is, curves space just like ordinary matter. We know we can't see it. We know it can't be charged particles, because if it was charged particles, when they're accelerated for whatever reason in a gravity field or otherwise, or in any electromagnetic field, they would emit light just like the aurora. And it's not atomic in nature, or we could directly sense it if it was in front of our noses, and it should be. So it's a mystery. So I want to say I did not make this chart up. Well, I made the chart up, but I didn't make the names up. Okay, so we don't know what this dark matter is, but you give things legitimacy when you give things a name. So we have a variety of particles here. We have WIMPs. And of course, if you have WIMPs, you have to have machos. But the WIMPs are weakly interactive massive particles. And what it basically says is what these things are particles that we can't see because they're weakly interacting. They're massive because they have gravity. And maybe they interact with the weak nuclear force, because a lot of things that interact with the weak nuclear force, like neutrinos, are very hard to see. Okay. Machos are an easier thing to understand. Those are massive, compact halo objects, and that's a fancy way of saying asteroids, rocks, comets, little planets, little black holes floating around, anything that has mass that's ordinary matter that we just can't see because it's too far away, or our instruments just aren't sensitive to it. And that's fine. Then we have neutrinos. We've talked about that. The problem with neutrinos is you need so many of them, but there are so many stars producing so many of them. So that's a possibility, but it doesn't quite balance the equation the way we would like. And then the last thing is there's a particle which is theorized called the axion, and it's a particle that was theorized because the equations of symmetry between quarks and electrons don't quite make sense unless you put a fudge factor in, and that fudge factor is an axion. Nobody's ever seen an axion, and very few people have even heard of axions, so maybe that's the answer, but I don't know. So we get to an important philosophical point here, and everybody here is probably familiar with Occam's razor, which basically says, there's variations of what this says, but the one that I'll take here is the simplest solution tends to be the best one, or the right one. Okay, Occam was a Franciscan monk, circa about 1300, way ahead of his time. So the problem with galactic rotation rates is very real. There's no issue with that. You can see that. You can see their Doppler shift. Nobody's taking any second opinions on that. But this invisible mass, think about this. So the solution to the rotational rates is we'll just throw in 5 times as much star stuff as is out there, and it's going to be really heavy, and then it's going to change the gravitational situation of galaxies and make them rotate at the right speed. Okay, that's a pretty simple solution, but maybe there's angels dancing on the head of a pin, and there are a lot of pins out there in the galaxy. I don't know. It's a hard one to stomach, but there's a fair amount of evidence for it, so I'm not going to totally discount it. And it is the majority opinion among physicists, by the way. So we have an alternative theory, and it was first presented by Professor Milgram. And it basically says, look, 100 years ago, Newton's laws were the end-all, be-all, and they were proven to not work under certain situations. Okay, they didn't work when stuff was moving too fast, when stuff was too massive, what have you, when stuff was too small. So they were modified by quantum mechanics and by relativity. So Milgram says, you know what? Why can't we modify Newtonian mechanics again? And so he came up with this theory which has been labeled MOND, which is modified Newtonian dynamics. And guess what? That explains the rotation rate problem perfectly. But it doesn't explain some other things, to be fair. Whereas dark matter doesn't explain the rotation problem perfectly, but it explains it to a pretty good extent. And it explains some other things and still doesn't explain third things. So along comes another physicist, a guy named Jacob Bekenstein in 2004, I believe, who said, you know, the problem with MOND is that we need a relativistic correction for MOND. And so he came up with this correction that was abbreviated TEVIS, or TEVIS. I'm not quite sure how to pronounce that. But what it stands for is tensor vector scalar relativistic modification to MOND. And guess what? When you apply that, all of a sudden the gravitational lensing is almost perfectly predicted. And there's a chart up here. It's a little hard to see, but you could see where MOND, especially with the relativistic fix, works better, and in some cases it doesn't work quite as well. What physicists will tell you is their one and only real great evidence for dark matter as opposed to MOND is this collision of galaxies called a bullet cluster. And the relativistic version of MOND, in fact, does explain many of the artifacts of the bullet cluster collision. And I won't go into that just because of time. But you could also see the dark matter and the MOND on the actual rotation rate chart. That chart that you see, the graph, is the distance from the center of the galaxy versus the velocity. So what we have right now is we have a situation where 5% of everything we see out there we could account for in terms of visible matter, stars, planets, whatever. Another 20% or thereabouts, I'm rounding things off here, are accounted for by this dark matter. And that still leaves a bigger problem, and that is that the universe is expanding. And if you have all this matter and you have all this dark matter, why don't you have all this gravitational contraction so the universe is collapsing? So there must be a third thing out there called dark energy. And I deliberately didn't put the picture of Darth Vader up there. This is not that kind of dark. So I mean, think about this for a second. So you got the Big Bang, right? And it's an explosive force. And it sends material out in all directions, very high speeds. But in the Big Bang, or right after the Big Bang, you still have mass and you still have gravity. So what you would expect is that this expansion of material would slow down. And then eventually one of two things would happen. If it started out fast enough, it would continue to expand. But if it started out not quite fast enough, less than the escape velocity of the Big Bang, for lack of a better term, then it would start to collapse and the Big Bang would turn into the Big Crunch. Well, neither of those are happening. So what's happening is it's expanding, but the expansion is getting way faster, and now we're something like, 14 billion or so years after the Big Bang, and it's still accelerating. So something is pushing it outward. So back in about 1929, Edwin Hubble made some measurements, and he used those measurements. He made the measurements the same way that we're talking about now with Doppler effects. And he found that the further away a galaxy is, the faster it's moving away from us. Now, that doesn't mean that in local clusters of galaxies, everything is moving away. It means in the macroscopic picture that the universe is expanding. And it's expanding at an increasing rate. And the rate of expansion is directly proportional to the distance. And that rate-distance relationship is defined by what's called the Hubble constant. So I've shown this before. And we could use it for the measuring the rotation rate of galaxies. We can also use it for the measurement of the speed of galaxies moving away from us. Okay. So I think I've talked about this already. So I'm going to bring in Werner Heisenberg, who is him with Edwin Schrödinger were really the founders of quantum mechanics, although there were a lot of other people involved in that, Max Born and Planck and a bunch of others, giving credit where it's due. And what Heisenberg said was, you know what? Quantum mechanics tells us that on the smallest scale, and since the biggest things also have the smallest scale property, just multiply it up, there's an uncertainty in your ability to measure both position and momentum, or a lot of people call it velocity, but it's really momentum, it's mass times velocity. So you have this uncertainty, and if you rewrite these equations just a little bit, you come up with another product term, which says you have an uncertainty in the amount of energy and the amount of time. And that's an uncertainty. That's called the uncertainty principle. And if a particle is standing still, then the product of that is 0. And since the product of that, it has to be greater than a multiple of Planck's constant. In this case, half of Planck's constant divided by 2 pi. That's what that h bar means. Then it can't, either term can't be 0, which means energy can never go to 0, even in a billion light years away in what appears to be vacuous space. So energy in the form of electromagnetic radiation is always present, and there was a great little laboratory experiment that was done a long time ago, and it's been repeated multiple times since. So this is not cold fusion, and this is not magic. It's for real, and you could repeat it at most college physics labs. And it's called the Casimir Effect. And so what Casimir said was, you know, we have this random energy in space, and it's at random wavelengths. It's at random frequencies. You know, there's some at light, and there's some in the gamma ray spectrum, and the microwave background, the cosmic microwave background, what have you. So if I take two metal plates and I put them very close together, what happens is the longer wavelengths can't exist because of the short spacing between those two plates. And the shorter wavelengths can exist all outside, so you got more stuff, more energy, if you will, outside of those two plates than inside of those two plates. And I would expect, or Casimir would expect, that those plates would now be pushed together. And guess what? They are. Okay, and he had an estimate for what that strength would be. And many years after he proposed this, in 1997, the experiment was repeated multiple times, and the estimate of the Casimir force turned out to be within 5% of Casimir's original prediction, which is phenomenal. I mean, attaboy. Okay, the problem with the Casimir energy is there's way too much of it. If you take these two plates and somehow you could put them, I mean, you can't in a laboratory, but if you could put them about 100 atoms apart, the force between those two plates would be about 15 pounds. Okay, so if the Casimir energy is the energy of the universe, if that's dark energy, then the universe would be expanding way, 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 way more than it's expanding now. In fact, the Casimir effect is 100 orders of magnitude too strong. And for those not familiar with the term order of magnitude, it's a 1 with 100 zeros. It's not 100 times. It's a trillion, 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 trillion. And I've lost track of how many trillions. But until you get 100 zeros out there, and a trillion has 12 zeros. So it isn't the Casimir energy that's causing this. Or if it is, it's some weird contribution of that energy, but it's unlikely. So let's go back to that cubic inch of space, and we look through the universe. And we know that there's quite a bit of energy in that cubic inch. There's the cosmic microwave background from the original Big Bang. There's the light from all the galaxies. There's stuff we can't see, like X-rays and gamma rays. And there's an occasional hydrogen atom in there. There's a lot of stuff in there. And if you remember that E equals mc squared, that energy and that matter is equivalent, which means that energy in free space could actually create stuff. So, you know, but wait, there's more, right? So the expansion starts at the Big Bang, right? And it increases speed the further out you go. And if that really happens, at what point do these galaxies start moving faster than the speed of light? Well, it turns out that they appear to. Now, the speed of light is 300 million meters per second. Einstein says no mass object can move as fast as the speed of light because it takes an infinite amount of energy to accelerate it. The reality is they're not moving faster than the speed of light. They appear to be moving faster than the speed of light. And remember that 300 million meters per second. A meter on Earth is not necessarily a meter at the edge of the universe. So a meter is longer out there. And so they're moving at less than the speed of light, but they appear by our scales of measurement to be moving faster. And so this is kind of a picture of this expanding universe here. The expansion started with the Big Bang. It increases speed the further out you go. And when you get to about 10 billion light years, the appearance is that these galaxies are moving faster than the speed of light. And the dark energy exerts the pressure that counteracts gravity, or what we're attributing to dark energy exerts that pressure. But that pressure is far more than the gravity, even with the dark matter, would cause the universe to either collapse or even slow down or either reach a steady speed. And this is kind of really hard to wrap one's head around. But it really is out there, and this is really observed. There's no question about it. You can question what the constituency of dark matter is. And by the way, the Tevis modification of Mond, that relativistic correction to Mond theory, also partially explains the dark energy pressure on gravitational expansion. And I could go into that, but it gets a little bit complex fairly fast. So I'll leave you in this talk with this thought, and I wouldn't exactly phrase it the way Martin Rees has phrased it in terms of we being nuclear waste. I like Carl Sagan's statement a little better, that we are star stuff. New knowledge is always being acquired. Theories that have existed and proved useful for decades or even centuries are being modified, and we saw that with quantum mechanics, and we saw that with relativity, and we see that with a variety of sciences. Science is never settled. Don't let anybody tell you differently. Things can always change. We saw how Newtonian mechanics was modified, and we could talk about the expanding universe, but the universe is by definition all things. So if the universe is all things, what's it expanding into? I mean, what do all things expand into? It has to be something else, and I don't know what that even means. So with that, I'll open it up to questions. Thank you. And thank you for coming out this evening.
Yeah, we're going to. Just wondering, what's the relevance that is expanding? I mean, other than just intellectually.
Well, I think it's more than intellectually. I mean, we always ask the question, what are we? What does existence even mean? And if we understand, it's one thing to understand the existence right in front of our noses and to understand our local existence and how we interact with our environment. It's another thing to really understand the nature of things. Religion tries to do that, science tries to do that, and I think it's important. And I don't think, by the way, that they're at odds with each other. And I think there's always going to be a question of what is. What is existence? And while this doesn't answer the question, it at least supports other questions that might be useful in subsequently answering that.
So does the cosmological constant in Einstein's general field equations model dark energy?
So the cosmological constant is kind of interesting. It was called Einstein's greatest failure or regret or whatever. And it turned out what it came from is his gravitational work in general relativity came up with an equation where if you didn't put the cosmological constant in there, you had a universe that was either expanding or contracting. And he felt at the time that the universe was stable. So we put it in there. And in fact, you can directly relate the cosmological constant to the Hubble constant. It takes a little equation to do it, but you can do it. The rate at which galaxies are expanding.
Could I come back to the macro scale or maybe it's the micro scale, meaning the environment we live in? What would be the current thinking about why the Earth's magnetosphere reverses?
Okay, so we see that reversal on the sun, and we see that reversal in our geological history, but you asked why, not how or if. It used to be thought that we had this spinning iron core in the center of the Earth, but that's no longer, it's hard to see what's in the center of the Earth. I mean, it's a long way from us, and you got to dig down deep, and we haven't been able to do that. But now we think it's convection currents in the core, and those convection currents become unstable at times. And that instability is a temporary instability, so it has to right itself. and it could right itself in one or two directions. It could right itself with north up, or it could right itself with north down. And so sometimes you just get a weakening field and then it comes right back, and other times you get a weakening field and it comes back the other way. You know, in the early days of spacecraft, we used to stabilize spacecraft with called gravity gradient stabilization, which was literally, no exaggeration, a Stanley tape measure with a ruler, with a motor on it. And so we would take this tape measure out and run it out with a little motor to about 30 feet. And since there's no gravity or microgravity up there, it wouldn't collapse, it would just go straight out. And then what would happen is the gravity at the end of that, if it was pointed straight up away from the Earth or straight down, would be a stable situation. And if it was pointed in any other direction, it would be unstable. So it would tend to orient itself. And 50% of the time it would orient itself down, in which case you would just retract it and send it out again until you got it right. That's an example of a quasi-stable situation. And the magnetic dipole is a quasi-stable situation. It's not a real parallel to the gravity gradient stabilization, but it is of that ilk.
So the sun's magnetic field switches regularly,
About every 11 years.
and the Earth's magnetic field changes randomly. At least we can't see the pattern.
We can't see a pattern in it,
'Cause
but
you-
we've seen
It-
a
when it
thousand
was-
changes.
There was like 20 million years, or no, 100 million years where it was the one color.
Right,
Yeah.
right. Yeah, so,
That
you know,
looked random.
it's a quasi-stable situation, and there is a random element, and, you know, perhaps if there's a geologist in the audience, they could give you a better answer than I can. All I can say is that whenever you're talking about convection currents and you're talking about thermal equilibrium in that kind of a process, you know, the result of that could be unexpected.
If the magnetic poles are going closer to the rotation poles,
They are right now.
then do they have to keep going to?
What ends up happening is it doesn't necessarily turn around nicely and smoothly.
Yeah.
It may start that way, and then the field actually collapses. And in
What-
fact, if you go to the southern anomaly, the South Atlantic anomaly, there'll be places where your compass will point the wrong way. So it's actually creating multiple fields, and then they'll reconverge into one. And I think if I could bring back
And we're all
that
going to
slide.
get roasted when that happens.
I don't think we're going to get
Sunburn anyway.
roasted, but you're going to find a little more skin cancers. You're going to find you want to use a little more sunscreen 100 years from now or 1,000 years from now. It's not the zombie apocalypse. It's not the end of the world. It's not great. You know, and a lot of animals use the magnetic field to navigate by. Yeah, it's not a great thing.
Getting back to the solar mass ejection, you didn't mention the 1859 Carrington effect.
Ah, yes, yes, very good. That was the strongest on record, and if that happened today, there would be substantial damage. I mean, really substantial damage. That was quite a bit stronger than the October 2003 event. But in 1893, we didn't have a massive power grid, and there weren't a lot of computers around. So the effect of it was auroras and radiation levels and things like that, but that's an excellent point.
I have a question, but
Sure.
I also have an opportunity to tell a joke. If I
Go
can.
ahead.
So my sister a while ago sent me this list of words, and you took one letter and changed it and gave it a new meaning. And one of them was the Doppler effect. And that is the tendency of stupid ideas to sound better the faster they come at you.
That's very good. I like that.
So my question was, you mentioned that some spacecraft or military craft, when they're in that South Pacific region, they're radiation hardened.
No,
So what is the material that earthly material radiation hardens a military
It's not
craft?
so much earthly material. It's that you can build a circuit that is far less susceptible to radiation than an equivalent performing circuit. It just costs you a lot more. Usually it's a higher voltage, or it's just a more robust metallurgy in terms of what makes up the transistors and the diodes in that circuitry. It costs you more. GPS and some other military spacecraft are like that, but GPS is in a much higher orbit. So it doesn't get down into the low Earth orbit. The problem is a lot of the environmental sensing spacecraft are down there. The International Space Station is down there. And there are a variety of other satellites that are down there that do a bunch of different missions. Most of the photography satellites are down there, whether it's US or foreign manufacture.
Testing. Yeah, I just wondered if science, at least Western science, might have tried to quantify this concept of qi in Chinese medicine that's regularly used in acupuncture, meridian theory, or also in the arts of Tai Chi or Qigong found in China, which is, I understand it's classified as something like energy on the verge of becoming matter, matter on the verge of becoming energy.
Well, that's interesting. I'm not aware of that, but matter can be on the verge of becoming energy, and energy certainly can be on the verge of becoming matter. I mean, we do that. We do that.
Just another quickie, since you're CAP, if I look at the navigation charts, the VFR navigation charts coming up the Pacific coast to Alaska, I'm frequently aware that there are notices that magnetic north is very different, maybe by as much as 15 or 18 degrees in different places.
Right.
Could you
So
comment on that?
there's two parts to that. One is the isogonic lines on the charts, on the aeronautical charts. And I'm not a marine person, but I am a pilot. So I don't know if marine charts have similar lines. I would suspect they do. And you can see, if you look at charts from 20, 30 years ago, you can see the shift in the isogonic lines. The other part of that is you talked about different magnetic, I'll call it variations, where you get into an area and north isn't the same way north is as 20 miles past. Now that can be due to several different things. It's often due to large magnetic deposits of minerals near the surface, but it can also be due, like in the South Atlantic anomaly, it's due to the magnetic field itself actually collapsing. And it's not so much a collapse, but it's turbulent, and you're getting multiple magnetic fields that are combining. So yes. If there's nothing else, I'd like to point to Dave Hydock, who's the squadron commander of Juneau CAP, Southeast Alaska CAP, and if you have any CAP questions, that's the man. Anybody? Doesn't have to be a CAP question, but it could be.
Prior to Vera Rubin, didn't Zwicky in the 30s observe anomalies and
They
galaxy
did.
clusters?
They
It was
did,
called dark matter.
and I'm not a historian, but my understanding was the observation was the result of the observation was correct, but the data was corrupted, and Vera Rubin was the first to actually bring forth an entire logical stream of data to conclusion. And I could be wrong on that, but that's what I've read. But yes, you're right. She is not the first one to observe that. She's the first one to publish a completely scientific and objective pathway to that conclusion. Well, thank you.